Jacob, on to you.
Awesome. Yeah, well, thank you for the intro, Juan. A real quick intro of myself. My name's Jacob Bauer. I've been at Devo for about 6.5 years now. Worked kind of all throughout the platform. I've been on the engineering side, been on the pre-sales side. So probably some people on the call that I've bumped into here and there. For those of you that I haven't met before, it's definitely very nice to meet you. What we wanted to talk about today, as Juan said, is kind of going through a walkthrough of how to write better queries on Devo, but really not starting there. Rather, kind of starting with how does Devo actually work behind the scenes, getting into a little bit of the nitty gritty of how our search platform actually behaves, how it ingests data, and then how searches are performed. And then we'll get into how to leverage that to actually optimize some queries and how to take your searches that you're writing today and just make them, do either that little bit or hopefully in some cases, a lot better than they're performing today, freeing resources and just making the platform run better for you. So I'm going to spend a fair amount of time in slides here. I definitely love doing more interactive demos, but as far as kind of describing how our architecture works and describing how the platform actually ingests data, we are going to stick in slides for that, and then we'll get over to the platform and query some data and kind of review some of the learnings that we have on the platform there. So without further ado, I'm going to share some slides here and we can get going. Let's hope that my slideshow loads. So, I did want to put a little bit of a teaser here, talk about a real world example that I've worked with, kind of reviewing similar principles and reviewing queries with customers. In this case, we had a query that a customer was performing over, I want to say, 90 days of data, and the search was taking 45 minutes. Now, you know, that is a long amount of time. Sometimes you need those answers, and that works great. But we're able to take some simple learnings from knowing how the query engine worked and reduce that search from taking 45 minutes to taking down to about 2 minutes, 95% reduction. So definitely not everything that you learn here is going to, reduce every search that you perform by 95%, but do want to show that this is real world applicable stuff. This is stuff that can make a very real difference, whether it's saving 95% or saving 50% of the time in searches. And yeah, we will be reviewing that. So let's get into what actually happened. So before we talk about searching, I actually think it's really important to review how Devo actually ingests data. In order to understand how we're going to search the data, it helps to understand how the data is stored in the first place. So what happens whenever you send data to Devo? So the starting point is that the data comes into some ingestion point. This could happen via the cloud collector, via relay, via any means that you're sending the data. Eventually, it's going to hit our Batraccio, and it's going to get sent to one of any nodes. For the purposes of today's session, we don't need to think about the nodes being spread out as much. We can basically think about everything kind of residing on a single node. Whenever we run the search, it's going to run the same process and do those. But wanted to put that there for accuracy. And then these within any given node, the data is actually laid out on disk according to a hierarchy of a file structure according to some different properties of the data. The most important one is the table that the data is being sent to. That's something that we determine from the tag on the data. So, in the case where we're sending in data from my host name to my.table, we're going to know that we should write that to the my table, directory structure. And the next part of how the data is laid out is by date. You'll notice that within Devo, anytime that you search data, you're searching for a specific date range, and it's something that's kind of fundamental to how Devo stores and ingests data. That one of the main indices that we store data in is, the date in which it was ingested. So anytime that you send data, we look at when that data was sent and we store that to the current day's, directory and to the current day's file. Now, I'll make one little note slash caveat here. And technically there is actually one more layer of indexing or splitting that is performed here behind the date structure, that can vary based on the data source. It can be splitting by things like host name on EDR data, IP addresses on firewalls, etc. But for the purposes of today's discussion, we're not going to get too in depth on that. We're going to remain primarily focused on, just kind of this hierarchy of structure. But again, I believe in kind of giving full disclosure on any little technical caveats there might be. So at this point, what's happened is data gets sent into Devo. We read out what table it belongs to, and then finally we append it to a file for today. And that's it. You'll notice here, as I'm talking about ingestion, I haven't mentioned parsing at all. And that's a really important paradigm for the Devo platform. We always ingest at query time, never at ingestion. And so, there's no need to interpret this log to say, hey, here's the email address and here's the action or any other logic on top of this. Behind the scenes, what we're going to store is the raw text of this message and that alone. And that's what will get appended to the file. So what we're left with, basically at the end of the day, if we think about a date ending, right? January 9th at midnight, the clock closes, and what we're left with is one gigantic file storing all of the logs for my.table for that day. We might have some successful logins, we might have some additional data on fields, various successful logins, failed logins, etc. And at the end of the day, what that's really sitting there on kind of one gigantic file, just stored flat as our data structure. Both at the end of the day and as time goes on, what we actually end up doing is we're taking this data and we split it into different blocks. A block is composed of a million bytes. It's not actually a physical separation of the files or the storage that's done. It's rather an ideological one where we go through and we say we split things up into logical blocks of a million bytes. And so block one might store the first, 10,000 lines of data here. Block two might store, 9,000 lines because some of those lines were longer. Block three stores some other data. But what this is really letting us do is split the data out into different pieces that we can later search. And this is important because we're going to next build up what's called the token index. Before we get into the token index, we need to talk about what is tokenization. Tokenization is our process by which we take a log and we split it out into the component parts, the component text parts that are that might be searched against. So worth noting, the token index is case insensitive. I said it's in uppercase here and there. I wrote my examples in lowercase below, but the example still stands. And what we basically do is we split on any non-alphanumeric characters, and we sort each of those tokens that is present in that log. It's worth noting there's some special handling for IP addresses where we can recognize IP addresses and store those as both individual tokens and as a whole token to speed up searching. It's worth noting there's a token max length of 20 characters, but what we basically do is for each and every log that's present within a block, we split up and look at the tokens that are present in that block. From there, what we can do is we can start to build an index pointer that tells us for any given token, where does that token exist in the data? In my example, I only have 3 blocks of data here, but in a real world example where a customer is ingesting, gigabytes or terabytes of data, right? There might be thousands of blocks here. And for each token that's present in the data, we store which block stores that token. We might have some tokens that are incredibly common, like the word successful, right? If we're reviewing authentication logs, probably every block of a million records is going to contain the token successful. It's just going to make up the bulk of the logs. But the really important part is we also have a lot of rare terms, right? A particular user's name might only appear in a small fraction of an organization's log, or a particular session ID is only going to appear in maybe one block out of the thousand blocks for that day. And so what this provides us with is a quick pointer where we can go through and we can say, hey, if I'm searching for something related to Nick, I can auto zoom in and just examine block 2 of the data. It lets me decompress and examine just that data without any further investigation. At the end of the day, all of the data is compressed, but as I mentioned, we maintain the ability to decompress any individual block, separate from decompressing the entire file for that day. And so what we end up with at the end of the day, and the reason that we can ingest so fast is these are the only operations that we're performing on ingest. It's just tokenization and storage of the data. It's worth noting on the bleeding edge, we update the token index periodically throughout the day, but we don't even there is the idea of a live token index, but we don't update it with every single log that comes through. And for the bleeding edge, we just search that data raw. So what you end up with here, as you're looking at data that's stored on the platform, you have a node. It has its data separated out by the table where the data is stored, has it separated out by date, and then we store all of the data that was ingested for that day, along with the token index that lets us super quickly highlight to look for rare terms or any terms that are present in the data. And at this point, data is ingested in the platform. You'll notice I hopefully have done a good job not mentioning the word parsing at all. It's worth noting, parsing isn't part of ingestion. And so at this point, our data is sitting here and we can do searches against it for anything that we need to do. Before we move on to the next section, and Juan, I'm going to defer to you here as well. I'm not sure the best way to take questions, whether it's via chat or letting people unmute their mics. I do want to just open up the floor to questions for a little bit to see if anybody has any questions about the process so far of getting data into the platform before we proceed to how data is actually searched on the platform.
Yeah, if you have questions, you can unmute or you can type in the chat. I'm more than happy to rephrase them or hand them to Jacob anyway. Whatever you feel more comfortable with, that's fine.
I see Surat has a question. Sorry if you'd like to unmute, or if you want to toss it in chat, whatever is easier for you.
Joel says we're clear. Right, here we go, Brandon. How is the date handled for a log that was generated a week ago but gets ingested today?
That's a great question. And so it's part of the paradigm of the Devo platform is the event date that the data is stored against, the leftmost column in any Devo table is always going to be the date that the data was ingested rather than some raw event date that was present on the data itself. So what that means is the data that was ingested today that has a timestamp, right? And any given log might have no timestamps present on it. It might have 6 timestamps present on it. It could be, EDR data. There might be, here's the timestamp where the actual event happened. Here's the timestamp where it was reported to the EDR collector. Here's the point where Devo ingested it, etc. But that data, when Devo ingests it, will always be stored on today, the latest time index. Now, what that means is whenever you do want to do searches against data sources where there might be delays or data might be coming in at different times, right? Not necessarily because of some issue with the collector, but in the real world, right? Sometimes data just can't get collected or a device was offline and then came online. What you'll always want to do in that particular case is you'll want to search for the appropriate time range where the data might have got ingested. So if I know that my data might be delayed up to a week and I'm looking for something that actually happened in the real world on, January 9th, I might actually have to expand my Devo event range date of search from January 9th all the way to January 16th and search that range. From there, I can further perform filters on there might be a field called timestamp. That isn't the date that the data got ingested, but rather the time that the event happened. And I can perform further filters based on that timestamp to look for the actual, range of data where my actual event happened. But I will have to set kind of that core Devo event date to the range where the ingestion may have happened, if that makes sense. And I think that actually answers Sarat's question as well. He asked, uh, um, "Is it based on the index time or the actual time of the event?" It is based on the index. It's based on the index time, the time of ingestion, not any timestamp that's present in the event itself. So hopefully that answers it.
Yep.
Cool,
I think you're good for
fantastic.
me.
Well, hopefully that's been enough time for everybody to, pose any questions that you have. If any others come up, we can still loop back into them later. But for the time being, I'm going to proceed with how does search work from here. Um, all right. So let's start with, I always like to think about examples. I have a search that I will perform. I just want to look for all logs where Jacob logged in and had a successful login, right? A super silly example here, but just kind of filtering on a few criteria to try and perform some data. Let's talk about the steps that are performed in the search. The first step is we determine what indices we can use. For the sake of indices, what we're going to be talking about too are kind of these meta indices, which include the tag, the date time, and those things, as well as the token index itself. Next, once we've done that, we can extract all data for relevant blocks. That's the point where we pull out all of the data that the indices have suggested might contain relevant data. Now, it's worth noting we don't know all the data that we pull out at that point won't be relevant, but we know that we've got at least all of the relevant data along with some other data as well. And finally, what we do is once we've got all that raw data, we actually start to evaluate the search. We do it in the query order against each line of the relevant blocks, and we only parse as we need it. So let's go through our example a little bit further here. How is my search going to leverage the index here? Well, the tag and the time index are both fairly straightforward. I didn't even include a date here in my search, but the tag index is going to let me focus on the fact that, hey, I only need to look at data in my table. And as such, I've already, just based on file structure alone, I've narrowed down, maybe the 6 terabytes of ingest on my platform to the 500 gigabytes a day that are related to, my.table login logs. The time index, we focus on the particular day where the data was ingested. And because the data is stored sequentially as well, we can also leverage that to narrow in on things. And then finally, we can focus on the token index. Now, any equality that's present in your search, we assume that there is the ability to leverage the token index there. If the username equals Jacob Bauer, then we know that the data, the raw data itself, will contain the term Jacob, Bauer, Devo, and Com. It will also contain successful login. And so we need to look at only blocks. A block, in order to possibly be relevant, has to contain Jacob, Bauer, Devo, Com, and successful. And so we can leverage the token index to be doing that. And, for this particular example, sorry, as I flip through slides too quickly here, as we focus on our sets, we say, hey, successful appears in these blocks, Bauer appears in these blocks, Jacob appears in these blocks. And so we can filter down to, hey, block 3 doesn't, sorry, I haven't included file here. That's a typo on my side. But I say, hey, block 3 doesn't include Jacob, so I can toss out block 3. That's not going to be relevant for my search. One little thing that I do want to mention here, in my case, I've provided an and statement. The token index supports any type of logical operators as well. If I did an or search where I said where username equals jacob.bauer at Devo or username equals juan.del Rio at Devo, what would happen is the token index would say, I need to find any blocks that contain Jacob Bauer Devo or any blocks that contain Juan Del Rio Devo. And so it will, and then it will take those groups together. So it's kind of, it does that type of Boolean logic evaluation against the data to be determining which blocks may or may not be relevant before the search proceeds. But at this point, what we've got narrowed down to are the blocks of data that we need to be evaluated. And we've done this in a fairly lightweight way, right? We've evaluated our token index. We've used our just base indices, which are built into the file structure. And so hopefully we've had a pretty lightweight lift to perform the search so far. What we need to do next is actually, kind of the more critical part of the search where we need to take those, blocks of 1,000,000 bytes of data each and actually perform the search against those. Hopefully, we've kicked out a ton of the data because it didn't meet some of our search criteria. But we now really need to find the needles in the haystack and take the million logins that happen and filter to just successful logins by Jacob. And so what happens here is that the search engine will actually proceed through the search step by step for each line, and it's basically going to be evaluating each and every line for these conditions. So it's going to start by, because of how I wrote my search, it's going to start by evaluating the username. The first thing that it's going to do is parse out the username, and then it's going to check and see whether it's jacob.bauer. So in this case, we'll parse out the username, see that it's blah blah at Devo. And at this point, the search is going to fail. Not fail as in the search will fail to return, but the search will say, hey, this isn't relevant data. This doesn't match my conditions, and as such, I can discard it and move on to the next line. So in this case, it doesn't even need to evaluate the status logic. It can just say, hey, my evaluation of username logic was enough to exclude this. The next line, parses out Jacob, or parses out the username, sees that is Jacob. Cool, let's proceed. Parses out the action. Hey, this is a successful login. At this point, we've done enough logic that we can say, hey, this is relevant data that I need to be returning back. We'll proceed. We'll notice the next point, the user will fail here, and it will, again, fail fast or recognize that it's irrelevant is probably what I should be saying rather than fail. But we'll recognize that it is irrelevant fast and not proceed further through the search. In the case where the user is Jacob but the action has failed, it will evaluate the first part and then go to evaluate the second part, and on evaluation of the second part, it will say, hey, this isn't data that's relevant, and proceed as well from there. And so why does this matter, right? What really matters here is that at the end of the day, and the reason that all of this is relevant to search operation is that the order of filters and the order in which we invoke parsers really does matter to Devo platform. A few other pieces about what we've talked about so far that are going to be relevant as well. But if we think about two searches that are doing the exact same thing. On the left here, I'm filtering to successful logins by Jacob Bauer. On the right, I'm filtering to logins by Jacob Bauer that were successful. We all know that those are the exact same thing. These two searches will perform differently on the Devo platform. Let's look at how the one on the left happens, or how the one on the left performs. The first thing that we do is we take the token index will point us to the exact same blocks of data for these two searches. The search on the left will take every single line. Maybe it'll take let's say that we have a total of 100 lines of data. It'll take those 100 lines and we'll check and see which of these were successful logins. Because we know that 90% of our data has successful logins, we'll end up passing 90% of that data through to the second operation. So at this point, we've performed 100 parsings. We've parsed the status 100 times, and we've evaluated the status for whether or not it equals successful login 100 times. The next thing that we'll do is for those 90 rows that got passed through that filter, we'll take those 90 rows and we'll parse out the username. And we'll evaluate whether or not it equals jacob.bauer@devo.com. And so there we're going to do another 90 operations. The end result is we'll have 9 rows. Nine rows will be successful logins by Jacob. But in this case, we've done 190, you know, parses slash evaluations of logic for performing the search. On the left-hand side, where we put the more selective filter first, we still start by taking those 100 lines of raw data. We parse out the username and we check and see whether or not it equals Jacob. At this point, because of our more strict filter being first, we only pass through 10 lines of logs to the second filter. Those 10 lines will will parse out the status, we'll check and see if it equals successful logins, and we'll get the exact same results. We'll still return 9 matching rows. But in this case, we've actually only evaluated the data 110 times. And so you can see there's a significant improvement to how we might expect the platform to behave against this data. And so this is really the lead into search optimization. What are the things that we need to think about whenever we're talking about search optimization? The first one is that when we can, we should use meta indexes, right? If we can search against a specific data rather than searching against all data, that's better. If we can search against, a union table instead of all data, that's good. So like start with a specific table if you can. If you can search just Okta data because that's where your relevant logs are, that's great. If you need to search a union table, which will search multiple different tables, but it won't search all tables, that's great as well, right? Search auth.all if the Okta data itself isn't sufficient. And then finally, only in cases where you don't really have any other resort, they exist. I'm not saying that they don't, but then we can fall back to the all.data to be performing searches across the entire corpus of data that's present in the platform. Next up, let's talk about using the token index. We talked way back here about, when the token index is used. Anytime that your search contains equals, starts with, or tokens, that clues the token index in that I can use the token index before I've even started to evaluate my individual search. If I'm doing searches like contains, weak has, or other operators like that, it can, in some edge cases, use the token index, but it's not always going to. And so anytime that I can leverage equals and has operators, or equals operators instead of has operators, equals instead of likes, that's going to give me better performance. And then the biggest thing that I kind of want to drive home is the orders of filters and operations. The more exclusive filters we can provide first, the better the platform is going to perform. And it's also worth noting, not all parsing and or operators are going to be the same. So the easier a filter is to evaluate, the earlier we should evoke it. So we'll talk in just a moment about that more in depth. So let's dive in specifically to orders of filters and operations, the topic I was just talking about. So whenever you're performing your search, and it's worth noting, right? This doesn't all have to be something that you get perfect the first time. This is something that I always find to be an iterative process. As I'm performing a search, I'll kind of maybe focus on a smaller time range and play around with what I think is going to be the more selective versus less selective filter first. But we always want to be focused on the more rare parts of the search. If I'm looking for, again, successful logins by a particular user, well, the bulk majority of my data is going to have successful logins. A small minority is going to be focused on a particular user. If I'm thinking about data for a firewall, right? If I'm looking for failed traffic coming from a particular source IP, while failed traffic might only be 20% of my data, or some portion of the data, it's still going to make up a double digits percentage of my traffic. It's still going to be present kind of across all time and space. Versus a particular source IP, especially if it's a rare one focused on a particular user's device or something like that, is going to really be that small slice of something that I can filter on. And so I'll want to be putting that username. I'll want to be putting that source IP as high up in the search as I can, so that the search can fail fast or can more appropriately, it can determine that data isn't relevant as quickly as possible. So that's really the main focus. The next one is really, really relevant too, which is to say, how easy is it to filter the evaluation? Um, the most important one that I want to drive home here is evaluation of lookup functions. So if I'm looking across all my firewall data and I'm looking for data where maybe there was a IP address that appeared in some threat intel feed, right? If I can be filtering on the data before even though only a small fraction of that data is going to come from malicious IP addresses, if my search has multiple filters, what's going to happen is every single row of data that makes it to the lookup evaluation is going to have to go and perform that lookup. And what that while that's a fast operation, it is still an operation that takes time. And so if I have multiple filters, I should generally be putting ones that are based on lookup data as far back as I can in the operation, because performing a lookup of data is rather costly in comparison with other operations. And that's really an important concept is whenever possible, move lookups later in your query in order to, and after filters to really speed up your searches. The last piece here of kind of ease of filter evaluation is there's a little trick that you can use. All data tables have a column that is called raw that will show you the raw data. The raw column skips all parser invocation. And so if you're wanting to do a search for what you believe is a really rare term, rather than saying username equals Jacob Bauer, you can actually make the very first filter in your search say contains raw Jacob Bauer. What that will do is the as the platform goes to perform its search, it will evaluate that search in order. And the very first thing it will do is it will say, hey, before I invoke the parser at all, before I decide how to interpret this data, I'm just going to check and see if in the raw string, Jacob Bauer is there. And that can actually really slice off a lot of time. Invoking a parser, depending on the table, can be, varying degrees of complicated. It's a very fast operation, but if we can skip it completely, it can really speed things up. And the last point that I really want to drive home here is, when in doubt, test on a short time period and then expand. That's my practical advice. That's what I always do. If I'm gonna go and run a 400-day search looking for multiple conditions across, gigabytes, terabytes of data, I'll definitely start with running the search for a day and trying out a few different operations of orders of operations, trying out a few different filters and things like that to figure out which of them performs best. And then I'll go up from a day to, 30, 60, 90, or my 400 days, whatever I'm needing there. So just a little bit of practical advice there. Now let's review some examples. These are, slightly censored, but real world customer examples. Here's a case where a customer was looking at all firewall data. They were doing a CIDR lookup to get a network name. They wanted to filter on a particular network, and then they wanted to focus on critical risk things. What was happening here is basically because there was the very first filter in the data was the network name, and so while the token index was focusing only on blocks that had core and critical, every single line in those blocks was getting evaluated against the lookup. By switching the order of operations and pushing the lookup later, plus leveraging that tokens clause, we're able to take a search across 400 days of data from 40 minutes down to 18 minutes. Now, 18 minutes, that's still a long search time, but if this is a daily search that's this is a search that's getting performed for some audit reasons or whatever, that's something that can be pushed to the background. And the most important part is by reducing the speed by reducing the running time by 56%, we've now freed up other resources for users to go and be searching the platform, got our answer that much faster. The other example that I presented at the front of the discussion without any explanation, but hopefully now we'll all understand, what's being done here is, we're searching all firewall data for successful or rejected logins, but coming from a particular class of users, these AAA user class. And then we're looking for multiple, login actions with more than 5 failures. The way that this query was initially written is that the very first filter that was put in place here is not null source IP. Now, in firewall data, sometimes the source IP will be null, but it'll be something like 99% of the time, the source IP is not going to be null. And so this is a very, very, very unselective filter. Basically, all of our data is going to meet this condition and continue through, while only a small fraction of our data is going to be, this AAA user authentication. So in this case, we pushed the more selective filters earlier. We said where lower action equals this earlier, and we leveraged the weak toktanes. And this is where we're able to get this huge speed up, right? This speed up from 46 minutes down to 2 minutes for this particular search, and really leverage, our knowledge about how the query platform performs its searches to get some real leverage here. So at this point, I want to get into a real world example, but I do want to open up the floor to questions here really quickly before we get to those. I'm happy to run over. I know we're only scheduled to run till 10:45. I think it's more important to get to questions and show real world examples, but I'd love to do both. Question in chat: how can I identify performance of query? The answer there is I think as Devo, we need to do a better job of providing back some query metrics, and I think that's something that we're going to continue to work on. For the time being, the most realistic thing is that you can just look at the time that a query takes to perform. One of my favorite tools for doing that is I do like to use the query app. I think there's going to be some feature parity coming soon in data search with this. But within the query application, you can provide a search that you want to perform. This is going to be my example one that I want to run. And I can come in here and click search. It's going to run the search for a desired time range. In this case, it's a 90-day window. And it's actually going to give me back some performance metrics for that search, the amount of time that the search took to perform, and that information. So here, if I hover over this little clock timer, this will tell me that this search, which for kind of as a sneak peek is our unoptimized version of the search, took 17.6 seconds to respond. Or sorry, actually the most relevant things here, 5.4 seconds says when did the API acknowledge my response? The final response is when did my browser get back all of the data? And then the render part is said, when did my browser show all of the data? For any small data sets, these two should be very similar. In the case where the rendered is much, much higher than the final response, what that maybe means is you're trying to pull back, a gigabyte of data into the browser to look at it, and it might be slow for the browser to interpret all of that data. So kind of this final response is the most relevant one. And we can look at the time for that final response to be evaluating how is my query performing there. Any other questions about this search performance? Yeah, great. Okay, so I have a question here from Tomas saying, can you explain again how the explain again the toktanes on raw and how looking up in raw is faster than that? So the important part there is that leveraging toktanes skips the invocation of the parser. Whenever we need to parse out a particular column from the data, it may take a number of steps of operations there. Let's say that we want to be parsing out the username from some CSV delimited data. What we need to be doing is we need to be searching that data for all commas present in the data. We need to be finding the appropriate occurrence of that comma and then pulling out the field that matches that particular um, piece and then be doing that matching. In the case of JSON, we might need to be diving 6 levels deep, and we might need to be interpreting a raw line of text as a dictionary structure, and then going and parsing out the individual components of some nested JSON to go and extract the key and value that we're looking for. And so, while it's not always the case, there are times that basically say, I just want to skip all that and I just want to evaluate the raw text of the message, where that performs faster. Especially, and it's really important to notice, usually whenever you have a really rare term. So searching for a token in a given string, um, there's a quick operation that can be performed there to just take a really quick pass and say, hey, is Jacob anywhere in this raw text? That might be much faster than going and saying, hey, interpret this JSON, pull out this field, and then see if Jacob is present in that particular field. I hope that that helps explain that piece. Again, it's a trick that's worth trying. It doesn't always work. If you're dealing with if you're dealing with a really fast parser, you might be better to just skip the toktanes completely. If you're dealing with a term that's not that rare, and most of the data is going to make it through your toktanes filter, it might not be worth using that. But in some cases, especially if we're looking for very rare terms, it can really be leveraged there.
Jacob, Joe had a question.
Yeah, Joel's asking. What I understand is better. Is that to optimize? You must know your data. It's often not the case that you don't know your data. Um, so if I got a query in a short time range, I may not find my results. So that's a great point, and it's definitely one that's relevant here. Um, if you're searching for something that you're searching a data set that you're not familiar with, um, you might not know which of these two terms is rare, which one isn't. Now, my general thought there would be this: look at the past day of data for performing your search and think about the different components there, right? I'm looking for I don't know whether or not a particular source IP or destination IP is rare, and I'm looking for all connections between those two. Well, if I want to evaluate that, right? If my search runs quickly, great. We don't always have to apply these rules whenever we're searching our data. If my search is running slowly and I'm still not getting any results, well, start to ask the question: does the past week have any data for my source IP? Ask that question in isolation. Does my data have any data from that destination IP? If I find a lot of matches from my source IP, no matches from my destination IP, and that's why I'm not getting results, hey, I've now kind of got that pointer telling me, oh, my destination IP is the rare one, not my source IP. If both the terms are rare, if neither of them's occurring over the past week, probably expanding your time range should work well. And that should be your search should continue to perform quickly because it's if neither of those IPs are present, it's just going to basically the token index itself will be able to parse out most of the data, and so uh, that's that piece. Um,
And then we had a grouping question. Samuel Mina.
Yeah, so Sam had a great question. How does grouping affect in performance here? And so I say that that's probably one that we're going to have to follow up on a future session. The focus of this was getting to the point where you've got the individual rows that match the filters. And the next part is kind of thinking about how the map reduce paradigm comes into play with grouping data and getting that data returned. There are some things that are worth considering, whether you're using data search or not for that determines whether the browser versus the backend engine are performing that grouping. A few other things there. Main thing I'd say, unfortunately, is a little bit out of the scope for the talk for today, where we're focusing more on getting to that filtering down the data. But definitely happy to come back and dive into that one deeper at another time. Um, And then, yeah, also, some questions about understanding the data. Yeah, it's is something where the fact that you do have to have some familiarity with the data is part of the reason that we don't magically do it, right? If the search engine itself isn't going to know that, hopefully there could be AI, ML features that let us, do a browse of the data and maybe get us some auto search optimizations or auto filter ordering to make those searches even better in the future. From there, I think that hopefully that addresses most of the questions.
Yes,
Um,
sir.
I still have at least another 10 minutes. I can even go past that. But we're going to walk through a really, silly example here in the real world. Show you I'm not just making all this up of running a search that we can keep making more and more and more optimized. Let me actually just make this run on a fixed time range. So what we're doing here is we're running a search against our firewall traffic. We're looking for denied traffic that came from a particular source IP, and we want to be evaluating it against a list of known public IPs, right? So silly example stuff. We want to be focusing on where we do have a match from the public IP lookup, looking for denied traffic. And here I really lazily, more just as a silly example, I said, tell me where the source IP is like this IP, right? Rather than equal to this IP. And so this search takes 17 seconds. I'm in a demo environment looking at 90 days of data. It is what it is, but this is definitely a search where we can start to apply some of our lessons from today to this. The most obvious one here is, hey, maybe I'm actually looking for equals for the source IP, not a like for the source IP. Probably not a real world example there, but nonetheless, by simply changing a similar to operator, that arrow operator, to an equal operator, I can make sure that we fully leverage the token index. And I took my search time down from 17 seconds to 14 seconds. I think in a lot of real world examples, that delta is going to be even larger there. Nonetheless, wanted to show that makes a real difference. I'll note here, I really hope the demo gods are with me because we're going to be talking about, you know, shaving off seconds as we go against a 14-second search. The platform is going to have some fluctuations, but all things equal, hopefully we'll be able to continue to shave some seconds off of the search. So right now we've already moved from 16 seconds down to 14 seconds. The next learning that we might be thinking about here is, oh, hey, we should be moving easier to evaluate filters earlier, but probably my reason and my source are easier to evaluate than a lookup. So in this case, I'm not changing the search that I'm performing at all. I'm still going to get back the exact same data, but I'm going to say, hey, let's take this reason and source evaluation that's being performed against the raw data, move that up earlier, move my lookup evaluation to later after I've already filtered down to the source IP that I want. And so with this change, hopefully we'll see the search perform a little bit better. It's all going to be trial and error, subject to little fluctuations. Who else is running searches at the particular time? But here, cool. We got our fractional improvement here, right? In this case, we move from 14 seconds to 11 and a half seconds, so 12 seconds, right? These are small movements that we're making here, but in real world examples, these really can be impactful changes. While we only move from 14 to 12 seconds here, this might be changing from 15 minutes to 10 minutes on that really big search that you're performing looking for an IOC. Or moving from a minute to 20 seconds on that alert that you want to write that needs to run every single minute. And so that movement from a minute to 20 seconds is impactful. The next movement that we might make here is we want to take our learning. So we want to say, hey, what do I think is a more selective filter? Um, Probably I'm going to have a lot of data on traffic denied. Instead, maybe this source IP is much more rare. I could go and run a query to check that, or I could just empirically test it here. Let's see what happens if I move my source query earlier. Um, I see a question in chat that Joel says, is there a caching mechanism that optimizes query execution from their second execution? Whenever you leverage aggregation tasks, there is. And I know that I think in some cases we do have some caching. There's some ability to turn that off. And in these cases, it's not going to be relevant here. I'll go back and undo my optimizations at the end to show that I'm not just getting better and better results because the same search is being run over and over. Um, the core answer is in general, there's not always caching that's done. I think it's something that we're continuing to look into and some features that we'll be rolling out in the future. But in general, there's not, and that's definitely not what's happening in the demo here. So by moving my source IP earlier in the search, we've now moved from 12 seconds down to 9 seconds. Cool. Again, nothing world shaking, shaving 25% off of my search time, but kind of all things factored in, we've now moved from 16, 17 seconds as we started down to 9 seconds. Cool. Worth trying now. Hey, I wonder if it's hard to evaluate the source IP. I wonder whether or not parsing that out from my firewall data, right? Maybe it's having to do a CSV operation to split the data and pull out different parts. I wonder if this might be a place where my toktains operator could be leveraged. So cool. Let's try it out. Let's try toktains raw and then provide my IP address. And we'll see whether, let's see whether or not this is going to speed up my search. Boom. In this particular case, we did have a case where evaluation of the parser itself was proving to have significant overhead in the total query time. And so what we've done in this case is we've actually moved that search time from the initial 16 seconds, 17 seconds down to 4 seconds, right? Cut 75% off of our search time by applying some of the various, lessons from today's talk to our session. Now it's worth noting this was a contrived example, right? I started with a particularly unoptimized query. I moved to something that was much more optimized, but it's still worth noting any one of these tricks are worth trying, right? If we flip around some of these operators, we move from least optimized to most optimized. There are grounds in between. If I leverage my toktains trick, that is actually providing a ton of the optimization here. It doesn't take away the fact that some of my other things still helped. Maybe if I can't leverage that toktain trick, it's still helpful to know that I can do this. Lots of pieces here to be considered. But at the end of the day, really wanted to walk through how each and every one of these pieces may or may not apply to any given search, but each of them should be helping to some degree. And it can be providing significant improvements to any searches that you're performing on the Devo platform. With that was kind of the end of the demonstration that I wanted to provide here. Sam asked a great question in chat. Do data types impact performance? In this example, string versus IP. The answer there is that there's it's a very vague answer. I apologize for that. Data types can impact performance, in particular if during the parsing of the data, it's having to perform some rather, quote unquote, heavy manipulation of data types that might be impactful. It can have impact, but your mileage might vary. There are probably some cases where data types aren't going to make a big difference. Let's see here, right? Like, it's a great question. I'm curious about it myself. Here's our search for checking whether or not the source IP equals this. I believe this. So this takes about 9 seconds. And my guess is we're probably the differences here are going to be negligible to be able to tell. It's not IPv4, it's IP4. Um, Here I'm guessing it'll be a negligible difference to be telling whether it's better to parse out the IP and then evaluate that against equality to an IP. Yeah, in this case, I mean it was a difference from 9 seconds to 8.6 seconds. Maybe we could test that a few more times or look at it over a larger time range to see if it makes a difference. And question is, it might be little differences on the data. It's probably not going to be something hugely impactful, but worth considering. Maybe worth testing as you build out your search. At this point, would definitely love to open her up for other questions. I hope that this has been helpful for everybody, just to take a little, sneak peek behind the scenes. I know some of this is stuff that I didn't know for a long time after working at Devo, and I do think it's something that really helped me up level my use of a platform. Um, Whether it's writing alerts that are going to be performing every single day, you can be lightening the load on the system by writing those better. Whenever it's writing that big search across 400 days of data, it can be making the difference between that search taking, you know, 45 minutes and going out for lunch while you're waiting on the results versus 5 minutes where you're just, able to microwave a cup of coffee if you're me, and then come back and get right back to work as you're ready for the next thing in your day. So, um, yeah, definitely happy to field any other questions. Otherwise, I just want to say that I really appreciate everybody's time today in coming and joining.